Hello, everyone. Many thanks to the organizers of the school for their invitation to give this presentation about the ITRF more than 3 decades of research and development for the benefit of science and society. But I will also address the organizers' request, and I will show you the ITRF definition, materialization, calculation, and contributions from techniques. I want to acknowledge the contribution of the ITRF team at my institute, IGN France. So this is the outline of my presentation. I will start by an introduction regarding the reference frame representation, taking into account the reality of an Earth that is deforming continuously, and also taking into account technique systematic errors and the user needs. I will then talk about the ITRF, its computation, and talk about space geodesy technique that contribute to its definition. I will focus on the ITRF 2020 and its innovation that models the non-linear station motions, seasonal signals, and post-seismic deformation for major earthquakes. I will show you how to use the ITRF 2020 kinematic model, and I will talk to you about the ITRF 2020 update. But let me start by recalling the definition of the International Terrestrial Reference System, the ITRS, following the IRS Convention. The origin should be the center of mass of the whole Earth, including oceans and atmosphere. The unit of length should be consistent with the meter SI, but also consistent with the geocentric coordinate time TCG. The orientation should be consistent with that of BIH at epoch 1984.0. The orientation time evolution should be ensured by using a no net rotation condition with respect to horizontal tectonic motion over the whole Earth's surface. In addition to the official IRS solution, the ITRF, there are 2 other ITRF combination centers delivering solutions such as the DTRF from DGFI and the JTRF from JPLO. Now, as you know, there are 4 techniques from space geodesy that contribute to the ITRF. These are the VLBI, SLR, GNSS, and DORIS. When realizing the ITRS by the ITRF, we need to take into account the various motions of the Earth that is deforming. We have 2 kinds of motions. One is the nearly linear motion that include tectonic motion and post-glacial rebound. And the other type of motion or displacement is what we call non-linear displacement that includes loading deformation that due to atmospheric pressure, hydrology, and ocean circulation. That includes also co- and post-seismic deformation, as well as transient deformation, volcano eruption, and local events. And we have also, as you know, technique systematic errors that should be taken into account when realizing the ITRF. For DORIS, the main major error is the mismodeling of the solar radiation pressure that leads to inaccurate determination of the geocenter component. GNSS has multiple weaknesses in recovering the Earth center of mass position and the reference frame scale in the absence of satellite metadata. SLR range biases have significant impact on the ITRF scale, as well as the VLBI and antenna deformation that impacts also the scale. Now, in terms of reference frame representations, taking into account the deformation of the Earth's surface, we have 2 kinds of reference frame representations. The first one, that's what we call long-term linear frame, which means that you have access to mean station positions at a reference epoch and station velocities. And you can map the station coordinates from the reference epoch T0 to any epoch T using velocities. And that's what we call regularized position with a piecewise linear function. But this is the indispensable basis for science and operational geodesy application. The second type of reference frame representation is what we call non-linear reference frame. And here we have two kinds. The first one is what we call augmented parametric reference frame, which means long-term frame plus non-linear parametric functions. And this is the case of ITRF 2020, which I will develop in this presentation. The second kind is the non-parametric reference frame, which means time series of quasi-instantaneous reference frames at the daily or weekly representations. And in this case, non-linear station motions will be embedded in their time series. But for this kind of reference frame representation, we still rely on the ITRF for at least the orientation definition. Now, the International Terrestrial Reference Frame is realized and maintained by the ITRF Center, hosted by my institute, IGN. It is computed by combination of solutions from DORIS, GNSS, SLR, and VLBI. The input solutions are in the form of time series, weekly solution from DORIS and SLR, daily from GNSS, and session-wise from VLBI. The whole ITRF itself is fundamentally based on collocation sites. And when we start the analysis for the ITRF computation, we start by time series analysis and stacking using CATRF software that's developed for this purpose. So the output will be station coordinates and velocities, but also other parameters. As I said, the ITRF is dependent on the availability of collocation sites. And for those who never saw any collocation site, this is the example of the well-known collocation site at Yarragadee in Australia, under the responsibility of Geoscience Australia, where we can see the 4 techniques that are operating at that site. In addition, we need local ties between the different reference points of these instruments. These are needed, of course, to build the ITRF and to be able to connect the 3 techniques together. Now, why do we need multiple techniques for the ITRF? For VLBI and SLR, these 2 techniques are fundamental for an accurate definition of the ITRF physical parameters or properties. SLR determine the air center of mass, which is the ITRF origin. SLR and VLBI define the scale of the ITRF, and VLBI places the Earth in space, which means that it ensures the link with the ICRF, the International Celestial Reference Frame. But their ground networks are poorly distributed and in danger of degradation. DORIS disseminates the ITRF in satellite orbit determination, and GNSS ensures the link between SLR, VLBI, and DORIS networks. GNSS is also the tool today to access the global ITRF by regions and nations using IGS products. Now, there are a number of resolutions on the ITRF, the IUGG in 2007 and in 2019, the General Conference of Weight and Measures in 2011, the ICG, the International Committee on GNSS in 2012, the UNGGIM in 2019, and we have also an ISO standard on the ITRF. Now let me talk about or introduce to you the ITRF 2020. And let me start with this introduction by explaining to you the strategy of the analysis we adopted for the ITRF 2020. On the left side, we have time series as input data from the 4 techniques, as I already mentioned. We have local ties, of course, and we add additional constraint at collocation site to equate not only station velocities, but also station seasonal signals. The strategy that we adopted is that we stack the time series of the 4 techniques altogether, plus modeling of nonlinear station motions, periodic signals, and in fact, seasonal signals, annual and semi-annual, and post-seismic deformation. In this step, in this strategy, we also specify the ITRF 2020 definition. The origin will be taken by SLR data, and SLR and VLBI will determine the scale of the ITRF 2020 and the orientation by alignment to the ITRF 2014. And in the bottom, you have the output of the ITRF 2020, station positions, velocities, post-seismic deformation parametric models, seasonal signals, and EUPs. The CATRF software, the ITRF combination model, is composed by 3 sets of equations. And the first set of equation here deals with the station positions, velocities, transformation parameters, and periodic terms. This set of equation is dealing with orientation parameters, and this equation is dealing with the post-seismic deformation model using logarithmic and exponential functions. Now, in terms of innovation for the ITRF 2020, that means precisely model non-linear station motions. So what we do, for instance, to model the impact of loading effect, we introduce a sine wave function where actually the unknowns are the A and B coefficient of this sine wave function, which means we add 6 more unknowns to the 6 unknowns that deal with station positions and velocities. In terms of post-seismic deformation, this map shows you 65 epicenter of these earthquakes that impacted more than 118 sites. And we model that by introducing parametric models, logarithmic, exponential, logarithmic plus exponential, or 2 exponentials, or 2 logarithmic functions. Now, just to give you an illustration of that, I take the example of Concepcion, the trajectories of the GNSS and the VLBI stations at that site before it moves to La Plata in Argentina. This is the Taigo system, actually. So here in blue, you see the original time series. In green, the virtual linear velocities that we adjust, together with in red, the parametric PSD model that we adjust using GNSS data. Then this adjusted model is applied the time series of the co-located VLBI station. And you can see how nicely the model adjusted using GNSS data fit to the VLBI station. Now, as I said in the beginning, the ITRF 2020 is an augmented parametric reference frame. And the kinematic model contains 2 parts, the linear part and non-linear part. The linear part, you know already, it is the classical representation of station positions and velocities. And the non-linear part take into 2 corrections, the sum of the post-seismic deformation for sites that are impacted by major earthquakes, and the sum of the seasonal signals expressed in the center of mass of SLR frame. Now, how to use that kinematic model, or in fact, how to use the seasonal signals. For precise orbit determination, we recommend to use the CM-based seasonal signals, because actually the ITRF 2020 provide these seasonal signals in the center of mass and the center of figure. So for alignment of global solution, you can use either one. That will avoid aliasing the seasonal signals into the transformation parameters, and the seasonal signal will be accurately retained in the aligned solution. If the center of mass is used, then the translational motion or the geocenter motion will be transferred to the aligned solution. And if the center of figure is used for these seasonal signals, the aligned solution will be free from seasonal geocenter motion. For the alignment of local or regional solutions, the center of mass or center of figure seasonal signal can be used depending on the user's needs. But of course, the common mode will be retained in the aligned solution. Now, the updates of the ITRF 2020, we did the first update that's called ITRF 2020 U2023. And the motivation for that is, first of all, the stability of the ITRF long-term origin evaluated to be at the level of better than 5 millimeter and 0.5 millimeter per year for its time evolution. And the agreement in the scale between VLBI and the SLR is at the level of 1 to 2 millimeter with no drift. The growth of extrapolation errors of the ITRF 2020 coordinates beyond the end of the ITRF 2020 input data, and the changes in the position of certain ITRF 2020 stations due to earthquake or equipment changes that occurred after the end of the ITRF 2020 input data. Now, the specification for this first update, we use 3 years of more data together with all the past data we used in the ITRF 2020. We use the same analysis strategy as for the ITRF 2020. One important thing that you have to keep in mind that we aligned the solution ITRF 2020 U 2023 to the ITRF 2020 for both the long-term frame and seasonal signals in the CM frame. And that is done for the origin scale and orientation. And the techniques, they use the same models and strategy as for their contribution to the ITRF 2020. Now, to do the alignment, we use the minimum constraint approach, which means that we have 42 degrees of freedom, 14 for the parameter of the frame itself, and 28 parameter for the seasonal signals. And in short, we apply no net translation, no net scale, no net rotation between the two solutions, the update and the original ITRF 2020. We do that using reference frame stations, and we were able to find 815 stations that satisfy that condition with the WRMS that you see here, which are for position velocities and annual and semi-annual signals. These all WRMS of the alignment are at the level of fraction of millimeter. Now we can also evaluate the origin uncertainty of this update from SLR, and you see here the TX, TY, TZ component of the geocenter, and we evaluate the uncertainty to be at the level of 1 millimeter and better than 0.1 millimeter per year. In terms of the scale, that is what we had in the ITRF 2020. The zero line is ITRF 2020, and the VLB over that zero line and the SLR below that zero line, and the offset between the two is about 1 millimeter in 1 millimeter at the equator. The situation in ITRF 2020 update, the first update, because we applied minimum constraint approach to align the two solutions, then we let SLR and VLBI free to adjust as they want. Now the zero line is for both ITRF 2020 and it is update U 2023. And as you can see, the VLBI scale change by minus 0.18 ppb and SLR scale change by minus 0.1 ppb. So roughly speaking, the uncertainty of the scale of that alignment is at the level of 1.1 millimeter in average. So in conclusion, more than 3 decades of research and development to improve the ITRF, it is the most precise and accurate reference frame available today. It is recommended by a number of scientific organizations, accessible everywhere, anywhere, thanks to IGS products. And the ITRF 2020 is a step further in improving the ITRF. We provide post-seismic deformation parametric models to deal with stations that are impacted by major earthquakes. We also provide seasonal signals in both CM and CF frames. And for the first time, the agreement between SLR and VLBI in terms of the scale is about 1 millimeter compared to 8 millimeter in the ITRF 2014. And the first ITRF 2020 update indicate that the origin and scale uncertainty between the two solutions is at the level of 1 millimeter. And the transformation parameter, and that you should keep that in mind, these transformation parameters between the two are all 0. And let me finish by saying that global geodetic infrastructure for the ITRF needs improvement and sustainability. Most of current VLBI and SLR system are old generation and need upgrade, of course. Thank you for your attention.